Use the second derivative test to locate the local extrema of the following function. So we've got a function here and we're looking on the interval from -2 to 2. Well, we are going to first find the first derivative, and that's going to be 12x to the third minus 12x to the second minus 12x plus 12, lots of 12s there. We're interested in where that first derivative equals 0 to find any critical points, because we see we have a polynomial, so it's going to be differentiable everywhere, so the derivative is not going to be undefined anywhere. Let's go ahead and factor a 12 out. That will leave x to the third minus x squared minus x plus 1. And we can factor that by grouping. We can take an x squared out of the first two terms and leave me an x minus 1, and we can take a negative out of the second two terms, leave an x minus 1. And so we can factor that. If we take the x minus 1 out, what that leaves us is x squared minus 1, which factors into x plus 1, x minus 1. So we'll have another x minus 1 right there. So it looks like we have two critical numbers, x equal -1 or 1. If we were looking at that, we would have -1 and 1, where the first derivative is 0. Now we could test numbers on these various intervals to see whether it was increasing or decreasing to determine if these are maxes or mins, but another way we could do it is using the second derivative test. That's what we're going to do here. So we're going to find the second derivative of this function, and that's going to be 36x squared minus 24x minus 12. Now what I'm interested in is what the second derivative's value is at my critical points, because if the second derivative is positive, I would have concave up, and concave up, I would know that I had a minimum. If the second derivative was negative, I'd have concave down, and I would know I would have a maximum. So let's figure this out at -1. If I put a -1 in here, by the time I square it, I get 36. It would make this one plus 24 minus 12. And the big thing I care about is it's positive. So I know it's concave up right here. And so this tells me that this is a local minimum, because we've got a critical number and our graph is concave up. Now looking at 1, I would have 36 minus 24 minus 12, which is 0. So the second derivative being 0 is an inconclusive test, so I don't know what's going on at 1 as far as a max or a min. I could go back to the first derivative and go ahead and test an interval on either side. So if I put 0 in the first derivative, I would have a positive. And if I put 2 in this derivative, I would also have a positive, and so it tells me that this was a saddle point. It was not a maximum or a minimum. What I was supposed to find is to locate the local extrema, and I actually had this restricted to an interval. We know we don't have to worry about the endpoints because we can't get an open interval around them for extrema, so the only place that I have is a local minimum, and that's going to occur at -1, and I can put -1 in this function to find that value. So that's going to be 3, and 4 is 7, minus 6 is 1, minus 12 minus 11 plus 1, so it looks like that's going to occur at -1, -10. Let's go ahead and look at this graph, and we see that we found the local minimum right here, and that was where the first derivative equaled 0 and the second derivative was positive, so we knew we had concave up and we knew we had the local minimum. Over here we did have a critical point, but it ended up being a saddle point. The first derivative was 0, so was the second derivative. That was an inconclusive, so we looked at the sign test.